Yeah. Today is a single neuron. It's called the perceptron in the 1960s. And the point is, it's just nonlinear regression. So there's nothing mysterious about it if you've never heard of this thing before. So it's called a single neuron because it imitates a neuron firing. So what do I mean by this? Normally, we think about regression is, we have y as a function of x, and we think about the f as a linear function. But the point about nonlinear regression is that f can be some much more complicated function. And that's the magic of deep learning, is that you hook up a bunch of these. So let's just take one. So a single neuron, which is back in the day called the perceptron, is a function called an activation function, usually differentiable. It doesn't have to be a smooth differentiable function at all. And in some cases, actually, you don't want it to be a differentiable function. But okay, whatever. And then you allow some weights and biases. I mean, these are just words. Basically, you have an affine transformation within a certain function. And then given this, you want to do linear regression. So a little bit different from stuff that you learned from before, from say Stats 101 in regression, is that you want to so normally what you do, you're given a point cloud of data, and then you want to fit this to some function, right? But in this kind of work, what you do is you usually take your data and you want to specify what is training data and what is validation data. Training data simply means the data that you want to train your regression on, right? And then validation is what you want to predict how good your validation, your regression function is. So this is slightly different from when you learn regression. Back in regression models, you're just trying to find the best fit. So training data is the one that you find the best fit, and then you try to find something on a complementary set of validation data, right? So what is typically done in machine learning is that I give you a data size, whatever it is. You split the data into training data and validation data. Most typically you take 20-80 split. You train on the 20% of this data, and then you validate on the 80% of the unseen complementary data. And this is called cross-validation. And normally, another very common thing to do is, how do you select this 20%? You randomize in these choices. So you give another arrow bar in your best fit. So a typical thing is called with five-fold cross-validation, which is I give you some data, whatever it is. The data is labeled. We're doing supervised learning now. So you have something to do your regression on. And then you take it into 5 chunks of 20% each. You train on 20%, cross-check, validate on the 80%, take another chunk, do the complementary. You do this 5 times, so it's called five-fold. You get an error bar within five times you do the sample. Okay, if your activation function is just a line, right, and then it's just old-fashioned linear regression, but with this extra caveat of cross-validation on splitting training and validation data. And this is clearly an example of supervised machine learning, because you're labeling your data with something. You have a point cloud, you extract one of the points, one of the dimensions, and then you label that with the remaining dimension. Somebody. Oh yeah, Vishnu makes a good point. I may have said it wrong. 80%, yeah, what I've been going extreme. So how you do the 20-80 split is up to you, really. I've been doing 50-50% split, but I think Vishnu is right. You train on the 40%, then you validate. 80% and validate on the 20. But as you wish. Strictly, I think it's right. You want to do whatever. I've been doing 50-50, randomized 50-50% sampling. So I just saw that on the chat window. So now I have a bigger problem, which is how do I get rid of chat window? It's all Vishnu's fault, just blame him. And then, right. So what are the most common activation functions? Right? So this is a list that I've compiled that at least the ones that I like to use. So the logistic sigmoid function, it's a hyperbolic tangent function. Now, why do we choose these functions? Because they look like this, right? It's the S shape. S shape is very good because that's what neurons do, right? The human neuron, well, in fact, pretty all biological responses are of functions of such a type. So yeah, you never thought the hyperbolic tangent was useful, right? But at least now it's useful for something. So then there are more, these we're familiar with from, math physics, but then there's some pretty funky names, but it's just like whatever. So there's this function called soft plus, which is a softened version of what's known as the ReLU. The ReLU is a very, very important function. It's called the rectified, this whatever, right? This is just names. It's called the rectified linear unit. And all it is this function f of x max of 0 and x. So it just goes like 0, and x between like this. And this is not a differentiable function at 0, but it's got a kink in it, but it's fine. It's continuous at least. And if you plot this function, it kind of looks like a smoothened version of this. So that's why it's called the soft plus function. There is the soft max function. Now, this is very, very interesting. So you map a list of values, xi, to a normalized version of this with respect to the sum of exponential. So it's a name. So this function is particularly useful when you have a multi-category classification. So for example, in the case of multi-digit classification, so I give you an image, and you got to tell me whether this image is 0 to 9. So there are 10, what we call 10 output channels, and the 10 output channels is very often given by functions of such a type, right? Because you only want the output to be one of the 10 values. This is a softened version of this, and then you can sort of round up or down into 10 channels. There is the parametric ReLU, which kind of, you have, it's whatever, it's a bent line. And there's, a max out, which is just you take the maximum over OX. And there's of course, the identity. But interestingly, I just want to emphasize, because we have weights and biases, the identity function is actually all affine functions. So you see what I mean? Like when I say the identity function, because of weights and biases, it includes all of affine transformations. So you should look in these, and also remember there's an affine composition with all of these as well. So these are probably the most common activation functions used. And chances are you probably won't use anything more fancy than any of these, right? So now that's the activation function, but what about the loss function, right? You need to do gradient descent to optimize something. Typically, this is also kind of standard in the literature, is that if you have remember I said there in supervised learning, well, in all machine learning, there's the continuous and discrete kind of machine learning. When your variables are continuous, you tend to use square error loss function. You always try to minimize function. What is this? Well, this is exactly the one that we're familiar with from Stats 101. This is the one which you try to minimize when you try to do regression, right? This is you take the function, with the function, this is the predicted value. This is the value, the actual value. You find the distance, find the square of the distance, and sum. And so that's the standard square. The squared error? A standard squared error. And this is a perfectly well-defined thing for you as your loss function. So this is for a single neuron. If you do continuous with this loss function, this is exactly what we used to call regression. For discrete variables, which is a categorical, for example, categorical classification problem. Like if you have a binary classifier, yes or no. This is great. This kind of problems come up in, say, NHS. Is the patient, do I need to treat the patient? Do I not to treat the patient, right? And then you use what's called the cross entropy loss function, which is this sort of kind of Shannon-like thing, and whatever, and you take this into your, you have the activation function, f, and you try to minimize this as you go along. So you try to regress with respect to this cross entropy function. And that's it. right? So that's the second of the three things you need, right? So with the first thing is the activation function. The second thing is what do you do given the activation function? You have this you establish this loss function. The final thing you need to do is a goodness of fit, right? How good is your chosen uh, activation function? For neuron, it's just a single activation function. For a collection of them, it's set of activation functions. And then what you need to do is, after you've done all this loss gradient descent, stochastic gradient descent on these functions like this, you need to measure. At the end of the day, you're going to spit out a value. Right? How do you measure goodness? Well, so remember this from Stats 101? I mean, this is so deeply buried into the depth of recesses of my memory. But somehow it is. For continuous variables, you have this so-called coefficient of determination. Whatever. I mean, there's a way to evaluate this loss, this value. The point is, you want this coefficient of determination to be as close to 1 as possible. So 1 is it's called the R squared value. So R squared is a good fit. If it's 1, if it goes to 0, it's crap. Right? And that's in the continuous case. In the discrete case, this is very nice. You have something that's called the confusion matrix, right? You're trying to predict, say, K categories. So you just literally have a matrix that says how many of them are matched with respect to the K categories. You want the confusion matrix to be as close to a diagonal matrix as possible. In a binary classification, we're familiar with this, right? This is like you see stuff like this on the news all the time, right? You have true positives, true negatives, false positives, and false negatives. And if you have a confusion matrix like this, and you have various measures, and that say, you basically want it to be 0 here, diagonal here. The generalization of the binary classification confusion matrix is a much bigger one. You can generalize this. So for alternative measures, if I give a matrix like this, how good is it close to being a diagonal matrix? Well, there are two standard ways to measure this. One is called the F1 score, which is this value. You can compute it. Just convince yourself, and you want this value to be close to 1 as possible. A little more sophisticated one is called the Matthews correlation coefficient. If you convince yourself, it's essentially the square root of the chi-square of the matrix divided by the size of the matrix. And you can check it goes to this. The Matthews correlation coefficients I like better than the F-score because it takes value between -1 and 1. If it's 1, it's perfect correlation. 0, random correlation. So it's like this randomly distributed. -1, it's exactly off diagonal. So that's like completely anti-correlation. So you probably should think of a switch of variables, right? So the MCC is a little more refined than the F1 score, in that it also detects the cases. It also tells you when to do anti-correlation rather than the correlation. So and another thing good about the MCC is that you can generalize to a K category classification, like digits, right? That's a 10 by 10 matrix, not a 2 by 2 matrix. In the 10 by 10 case, you can convince yourself it's this expression. You can code this up. I mean, I coded this up in Mathematica before I realized, all of this is built in Python. And all of this is now built into Mathematica's, beyond Mathematica 12.5. I know mathematical physicists like to use Mathematica. Anything beyond version 12.5, all of this, it's inbuilt. So you don't need to do anything about it. So everything so far is, as I said, the sort of the principles of regression, nonlinear regression, but with the extra twist of training validation and then these measures of goodness of fit, right? So here comes the magic. The magic is this philosophy. I'm going to go back to support vector machines in a minute. This is kind of amazing if you really think about it. And there are theorems, deep theorems proven about this. And I'm just going to cite this theorem because I certainly haven't gone through these theorems in any detail. The point is, if you hook up a bunch of these activation functions in a network, that's why it's called a neural network. And the simplest case of such a neural network is if your graph is a unidirectional graph. So such a case is called a multi-layer perceptron back in the day in an MLP. That word has fallen out of fashion. It's now generically called a FNN, a feed-forward neural network. You can certainly have arrows going backwards, and they're usually called recurrence networks, and that certainly it's fine. But a structure like this is already extremely good for predicting generic things, right? So this goes back in the day, I don't know, in the 80s, this is called connectivism. I think connectionism or connectivism, which is that if you connect a lot of bunch of things, it tends to approximate any function. So that's the basic idea of connectivism. So I'm going to state 3 theorems in a minute, which actually make that a precise mathematical statement. But intuitively, you think, right? This is the entire, foundation of neural network. Is that given a simple function like this, if you create a network of such functions sufficiently complicated, it should approximate anything, right? That's the underlying principle. It's not obvious that this is true, but this is actually quantifiable. And then a lot of the neural network research is on this. How good is this? What are the approximations? How fast is it? What is the convergence rate and stuff like this? And that I don't do any of that. I take that as my input in my research. I don't think about it. There've been recently very beautiful papers by let me try to think. Hashimoto, Jim Halverson, Demela Kok, who's South African, where they tried, because they're physicists, they tried to understand this connectivism from the point of view of renormalization group flow, where they try, and Dave Berman is involved in his written papers on this as well, where you actually try to write this large network and then try to model it in terms of some quantum field theory. That's a very nice idea. It's certainly a very novel approach to neural networks. So that there's sort of a new growing community where quantum field theorists and neural network experts are talking to each other. Just another few more jargons. In a feed-forward neural network, the depth is usually this direction, roughly this direction, and the width is roughly this direction, right? Roughly. So when this direction becomes very, very large, it's called deep learning as opposed to just normal machine learning, right? I mean, it's jargon because you want a deep learning. So here are the theorems, and I'm not going to read out them. They're very, very boring because they are they're stated in this extremely precise analysis language. But hey, you know what? The basic idea is that due to these people, they basically showed with large enough this direction or large enough this direction, you can approximate any input up to some given measure. So there's some Lebesgue measure of integration. What is truly remarkable is Hanin's theorem on the ReLU theorem of Hanin, which is basically is that even with the ReLU function, so this is a simple, this function here, not the parametric, this ReLU function, it's max of 0 and 1, right? This function, if you connect enough of them, this theorem says it's good enough to approximate anything. And that really is true, right? The point is that approximate anything. Now, I mean, not just continuous outputs, right? If you have a single perceptron, you end up, approximating continuous functions or even smooth differentiable functions. But this idea is that, in nature, that doesn't happen very often. And this is another magic of this whole idea of AI, is that most things in nature are not well behaved. They're not, sine, right? They're usually extremely complicated functions. But the magic of Hanin's theorem is that if you link up enough ReLU in large enough depth and large enough width, it will approximate anything, like literally anything. So you can read this, blah, blah. Of course, there's some conditions of convergence, blah, it doesn't matter. And I was trying this, and it's really true. I was trying just ReLU networks. I'm just in some couple of layers, five layers, each about 5-10 neurons. So 5 by 5 it's not very deep learning, right? Then I tried to approximate just using ReLU function to compute cohomology, the ones that I mentioned earlier, which is, if you think about what you have to do back in a computation like this, I'm not even sure I mentioned it. Like if you want to compute H11 of a manifold, right? It's not. I mean, you got to do some serious sequence chase, right? And the idea is that a lot of these steps, I mean, all of the intermediate steps are nonlinear because you're dealing with nonlinear polynomials, and there are a lot of jumping phenomenon. There are regions in moduli space in cohomology where the answer suddenly jumps, right? In codimension 1 hypersurface is codimension 2, and then suddenly your cohomology. This is a generic problem with cohomology. It's just like it's not a smooth function. The bits here it jumps, bits there it shifts. I mean, at some level, the entire foundation of sheaf theory was invented to try to accommodate such cases because they jump so badly. So if you use a ReLU network to try to predict this, surprisingly, it works pretty well, right? It shows that there's some underlying structure to computing cohomology that mathematicians don't even know about. And we don't know, but somehow the neural network is approximating it. And it's approximating it is in a way that's not a surprise, because after all, the stuff coming out of there is very structured. And Hanin's ReLU theorem says that you should approximate it very, very well. So this was a very surprise. This was very surprising to me. But hey, it is what it is. So everyone happy? Happy? So okay.
There's a question, yeah?
Yeah.
So is it okay to choose different activation function for say different neurons in a neural network?
You mean to have a mixture of activation functions?
Yeah.
Yeah, absolutely. Absolutely. I mean, the generic case, you will use completely different ones, just up to taste. And there's a lot of black magic, right? It was like, why is it, a hyperbolic tangent followed by some ReLU, works very well. And I mean, this is a huge area of research, in what structure it will do well. But Hanin's theorem, it's just that it's good enough to use ReLU, but your neural network could be extremely large in both ways. This is basically the large n limit, right? So it does that. But I was surprised that ReLU was good in the small n, where n is very small, that it works. But absolutely, in the generic neural networks architecture, you have a complete mixture of these things, at least these things, right? And
within the same layer?
Sorry?
So can the activation functions be different even within the same layer?
The activation function stays, sorry, in the same what? I didn't hear the last.
Can they be different within the same layer?
Oh yeah, absolutely. Yeah, absolutely. Yeah, absolutely. You can do mix and match. You may not want to do it. It complicates things, but you can absolutely choose. You want to choose a hyperbolic tangent here and a ReLU here. That's totally fine. Totally fine.
So what's the difference between having, like, say, a really large number of neurons in a single layer versus different layers with the same number of neurons?
You mean like different, so each layer has a different number of neurons?
Why have so many different layers of neurons? Just have one layer with the same number of neurons.
Just have one layer. Yeah, I mean, I guess, and then take the infinite width limit. Is that what you mean?
I guess the question is keep the number of neurons the same, but increase the width and decrease the depth. Is that the same?
Yeah, that's fine. Yeah, that's fine. And there people write papers about, if you take a large M limit this way and take a small K limit, how well does it behave with respect to the other direction? That's a lot of the research is done on this.
And presumably you need at least two.
Yeah. Okay. You don't want to go too extreme. If your output
one,
layer, exactly. If you're outputting just a single number, you may want at least two layers. May want all of this going to one. I mean, just to input. But just try it out. I tried the classification problem of say like some in a small Hodge number range, and I tried to do some prediction like that. And usually 2 is not that great. If you just have 2, it's not that great. But that's just from experience. But I didn't try the large width limit. And you can also, of course, tune various other things, right? And one of the things that is exactly what we get to now, which is, you know, all sorts of various things that you can do in the middle. And this is, I mean, there's a whole art to this, which I'm a complete novice in. I won't go into too much of this. There are all these hyperparameters you can tune, right? Meaning, for example, learning rate, which is this thing here, right? That you can tune that, which is step size, basically. You can specify during your training procedure. And, you know, you can do other things like one of the biggest things that you always want to do is you want to regularize and prevent overfitting, right? Overfitting is a serious problem because I mean, let's think about how many parameters are here, right? If your data is only 1,000 points and you put a couple of these and each one of them has, you know, these are weight matrices. If you got to make sure you don't have more hyperparameters, you know, W and B, these bias things, they're all hyperparameters. Which which are parameters that you need to determine in addition to the hyperparameters like learning weight you can tune. You got to make sure the degrees of freedom doesn't exceed the actual number of data points, right? So some of the things that people do to try to prevent overfitting, one is, well, obviously, you can overfit a training set. It's not too terrible because the validation set makes sure that you're not overfitting. Right, you see what I mean, right? Because you can completely overfit with respect to a training set, but then if you have a validation that you've never seen that before, so that at least is a good check. But you don't want to even overtrain on your overfit on your training set because it's just bad practice. So some of the things that people do, some standard things that people do are like called dropouts. You know, these are all cool names, right? You know, dropout simply you switch off some neurons at random to kill off some of the parameters. And then you can do things like early stopping, because you can. One of the things you can also do during training process is in training validation. So even before you do the full check-in with the validation data, you want to take a small sample of the validation data and you just try to check it at every step to see whether it's actually you know, it's actually learning the whole thing and it's not predicting things you haven't seen before. So you can do a little bit of it. And if it gets increasingly worse in the validation error, you can just stop the training and try to do. And these are just various things that you do. Other jargon that are just words I've learned. Right? An epoch is one round of training. You want to do multiple rounds. And I mentioned batch size because sometimes even the training set gets too big. Sometimes I think batch size is sometimes called mini batch size. So you want to split your training set into batches and the number of iterations as you go through this training set into this training, and then each round as you pass through the entire training, it's one epoch of training. These are just words that you use. So these are just some jargons, and back to neural networks. So I guess two of the most important architectures. So the choice of which ones you put, which neurons you put, which activation function, your choice of the size and the width and the depth of the neural network, it's called an architecture. So the two of the most commonly used architectures are CNNs and RNNs. So CNNs are convolutional networks. This is pretty much the entirety of the field of image recognition. Every image recognition problem is at some level will use some fancy version of a convolution network. And what the convolution network does is that it has a layer that does, because what's an image, right? Image is an n by n grid. Each pixel, so right, each thing is called a pixel, and a pixel is if it's grayscale, it's a number between 0 and 1. If it's colored, it's a triplet of 0 to 1s, telling you the percentage of red, green, or blue. So that's what an image is. So a grayscale image is an m by n matrix of what we call mn pixels. Each entry of a matrix is between 0 and 1. That's a grayscale image. In fact, if you can do this. One thing I really like about Mathematica is that you can take an image, take your favorite image. I don't know, take a picture of Yao. I don't know, take a picture of. So we all have pictures of Yao in our rooms. We worship, and then you take that and you just put it into Mathematica as a GIF, and you just say convert to a array. I think it just / array, and it will literally give this in terms of a 256 by 256 matrix. Now, if you like Yao even more, you have colored pictures of Yao in your living room. In which case, if you do take the GIF, you can just look at here's a colored picture of Yao / array. In Mathematica, will just spit out a 256 by 256. I'm saying 256 because that's the usual choice. A tensor. Each entry is a 3-vector. And each entry of the 3-vector is 0 to 1, because that's the percentage of red, green, and blue values. So what a convolutional network does is that at one layer of your neural network, it takes this input structure, this matrix of values, and it creates a smaller box, and it goes through them like this, right? And that's the convolution, right? That's all it does. Well, I mean, there's fancy ways to write this, right? But this is this. This is the Bourbaki way of writing it. This is the Arnold way of describing it, right? It's just doing that. And then it's basically recording the value of this, right? So why is this useful? Because it tells you the relationship of neighbors. Apparently, humans recognize pictures because they don't just see the picture as a whole. Somehow our neural pathways are trained to see how shading happens, how close your eye is to your nose. And the convolution takes care of this particular direction, right? So all image processing neural networks will at least have a layer that looks like this. Okay. I won't bore you with RNN. So that's kind of fun. So everybody's happy about NeuroWorks. And the most important thing is I just encourage you guys to do it. If you're a Python guy, go to PyTorch or scikit-learn, and everything here is built in. And what's really wonderful is beyond Mathematica 11.1, all of this stuff is built into Mathematica 11.1. And of course, we like Mathematica, and then you can just do this on Mathematica. In fact, I can even show you an example. Right? So I thought this is no, okay. This meeting is recorded. I can show you an example here, which is this example here, which is a wonderful example. Now I have an extra challenge, which is to share this share, right? This is Mathematica. At some point I switched to. Can you see my screen?
Yes.
I can see. You can see my Mathematica notebook, right?
Yes.
Yeah, great. So at some point I completely switched to Python because I thought, well, all this is great. But here's a little trade secret, and Wolfram isn't paying me for this. But in most of the stuff that I do now, I find Mathematica just as good as PyTorch. But shh, don't tell anyone. So here's a perfect example. So what I do here, right? So I take Mathematica has the built MNIST database. This is the database that I mentioned earlier about stuff. When you just got stuff that's been recorded since the 1960s. It's got everything. For example, I take this MNIST database on training data of handwritten digits. Okay, let's hope to God that this works, right? And that all that is the table of associations of handwritten. This is an image, which is in this case 28 by 28, which is a grayscale, right? And some poor graduate students had been doing since 1960 to associate this, right? So now let's just pull like a sample size of say 100 of these, and then I'm going to construct a neural network. In Mathematica, the command is just netchain, as I promised, the convolution layer. Right here, I put 2 convolution layers. This structure was found. This is a standard one. I think this particular ramp is the ramp function. I can't even remember what it is like myself. Maybe it's like this. And I finish with the softmax layer. Remember, the softmax is a categorical classification layer. I have a categorical problem of 0 to 10. Right. So let's just try it. It'll never work. So I'm taking a sample. It's finding resource, it's going to MNIST, and it's pulling this down, this handwritten digits. Okay, so now my samples look like this. Some random data of 100 sample digits. Right, this has been labeled by poor graduate students since the 1960s. In this case, do I even see any misclassifications? I don't think so. Right, I think that these are all pretty good. Then I establish this neural network of convolution layers, and that's that. And then I train this with my sample, with my random sample. And you see, it does all this fancy stuff. I mean, it tells you about the training of the loss function. This is a good sign. If it's going like this, you're doing great. If it's not going like this, you just change your architecture, right? And it gives the error rate. I mean, it really is very good, right? It tells you Adam is a standard optimization technique for selection batch, and your learning rate. This is your step size, and it tracks your loss and error as you train this procedure. And it did however rounds was. That was 1,000 rounds. I mean, this is on my laptop, right? This is pretty impressive. Right? How long did that take? 1 minute. Right. And now you can do validation on. I take a random validation, which I take. My data is very big. This is some MNIST data. I take validation another 1,000 random samples. So now this is my validation is kind of different. Like let's take like from 3 to 400, right? So it's a different set. The idea is now I've trained on this. Can I predict, how well do I predict on these suckers? The stuff I've never seen before. Well, so I can do a wonderful thing, which is just this. So what this does, if you're familiar with Mathematica, I apply the net to the validation value, which is the first validation value, which is the picture, right? And I compare the number of cases that it's equal to the second one, which is the correct value. And I see how much out of 1,000 this has worked well. And it works well because I'm actually evaluating the net to the thing. Okay, so within a sample of 100 training, just 100, and then I tried on a data size of 1,000, I have predicted 788 of them correctly with this convolutional network. That's pretty good, right? If I up this 100 sample to like 500, it'll do much better, and you can play games like this. So the idea is this is the same. Of course, it doesn't have to be. I've given you this MNIST data. Some of my more favorite data is well, of course, my favorite data is if I can ever find it, it's something like this, and it's. You can see here. Can you see this?
Yes.
Yeah. So do whatever. Here's another data that I try to do. Like here's the list of. Here's something more relevant to us. That was handwritten digits. This is something more relevant to us, which is I take all. Remember, I told you about the hypersurface Calabi-Yau data. So this is a list of 5 integers. And their Euler number, H11, H21. So this is a list of 7,855 of these. This is the quintic, right? So that's, you can see the total length. Here's a random one. So this is this is funky, right? This is a degree 5 plus 6 plus 6 plus 28 plus 39 hypersurface embedded in weighted projective 4 with weights like this, whatever. Thank God, Philip. Thank you, Philip, for providing us with this goodness and the abundance of thy data, right? And then this is Euler number 0. So this is a self-mirror manifold, which in some sense. And I attach Hodge numbers H1 38, 38, which is random sample. And you can plot the distribution. As I said, distributions of 3 and 4 is this is H11, H21. They're all Planck. I don't know, life is Planck. This is general theorem in life. Life just tends to go in Planck. This is Euler number, so it's a little more balanced. So what can I do? So for example, I wanted to predict, say if I wanted to show you an example of a binary classification. I want to see whether this has large volume structure or small volume structure, right? So I make anything that's bigger than H11 equal to 50, 1, anything less than H11 to 50, 0, right? We can do that. Now it becomes a binary classification problem. Of course, if you want to do the full H11 classification, that's fine. People have done this now. People, especially like Finatello and friends, they've done beautiful work using very sophisticated network structures to predict the full actual H11, H21. But here, let's just do a two-way, just make things easy. So this is a fairly balanced data. There's 3,000 cases, which is 0, 4,000 cases, which is 1. So that's large H11, small H11. And if you plot, it looks kind of, so here's a bit. So that's it. So this is the data. Here's something interesting. If you do a PCA analysis, it plots the ones that are large and the small ones which are small. And it kind of separates, but not great, right? You don't see two separation blobs. It's kind of like this. Now, know what I'm doing, right? I'm taking a 5 vector and I'm trying to extrapolate the 2 principal axes of this 5-dimensional thing. There's no way for you to visualize this, right? So it's kind of separates up, but I wouldn't use a PCA to do this one because it's not separation. It kind of looks cute, but I can't really separate anything. But what I can do is to establish a neural network to try to do the classification. Again, I do cross validation. I take sample of 2,000 cases and take the rest 6,000 to be what am I doing? To be the validation set. And in addition, I'm going to do a yin training validation size of 500. So I'm just going to randomly sample 500 to see how good my training process is. Instead of testing against all 6,000, I'm going to test it against the 500 cases. So I pick, as I said, so this may answer your question. Here's a completely random set of stuff, right? So I begin with a linear layer. So a linear layer of 500 neurons. It's quite big. Hey, whatever. Then I take all of this linear layer to fit it into a sigmoid. Then you can do whatever. You can put that sigmoid into a tangent if you want, and then do a linear layer of 2 because my output is 2-channel, right? It's 0 or 1. Then I do a softmax, right? So to make sure it's 2. So there are beautiful things you can do in Mathematica. You can show the summary graphic, right? And that's so let's just try it. So let's do this net. Let's hope to God it works. And now I'm going to do the training process. Okay, so something's going wrong. Ah, crap. Okay, let's try another network. Whatever. Try this another ramp layer. Let's hope it works. Yeah, there we go. Ooh. Okay. On a good day, you will see that it works. This is not one of them. Let me quick kernel. I should work. Quick kernel. Quick kernel. Okay, let's truly test whether this is a good day or a bad day. Okay, so this is fine. I'm reading the data. I cross-validate the data. I split it, and I did just sort of did. Okay, sorry. Okay, and I'm missing some IDDs here. And I do the validation. I do a network train, and ooh, that's weird. It did something for a second. Anyhow, on a good day, you can retake this and you'll see it works. Well, hey, last time it was where maybe it's because Mathematica updated during the last time I showed this demonstration. But you get my point. But thank God the digit classification problem did work. So I'm going to go back to
Where did you get that database you're reading from for the Calabi-Yaos? Which one is that?
That one is the weighted hypersurface data, and it's available. It's available. Just type weighted Calabi-Yau database, and it's freely available.
So you have to import it into Mathematica. It's not there in Mathematica.
No. Yeah, no. I think I might even have put that online somewhere. I can't remember, but certainly it's on GitHub in Python form because my former student Ed, has organized a lot of this, and it's on GitHub. Now I want to do something. I want to share again. I'm going to go back to trying to find out what the bug was about. But first, I need to be able to share again. Yes. Right. Should I go into? No, I think this is good. Right. So I have 30 more minutes, right?
Yeah.
Good. So in the last 30, I think okay. In the last 30 minutes, oh yeah. So this this is the thing. This is the data I was trying to describe, right? So if it had whatever I did earlier worked, you should have gotten curves that look like this. And the training curves will look something like this. And this is more seriously done in this paper with Berman a couple of years ago to find new structures in this 5-vector. Sissies I like because I said everything's an image. So sissy you can put in an image. It's kind of pretty, right? A typical sissy looks like this because you can do multi-graded colors, right? You can say 0 is purple, 1 is green, and then you can pass through it. But this is the basic reason why algebraic geometry responds so well to machine learning. It's because I say sissy because I'm biased by Calabi-Yau manifolds, because whatever, any algebraic variety is an image. I've said this in front of algebraic geometrists and I haven't been killed yet, so I think it's fine. I said, the entire field of algebraic geometry is image processing. And then I went even more hardcore and I just go around and said, mathematics is image processing. And so far, nobody has killed me. And they said, well, at some level, it's true, because what is mathematics? Mathematics, the entirety of theoretical science is about processing the Turing machine. Your input at some level is zeros and ones, right? And you can even put a little more structure by turning them into images. The only people who've ever disagreed with this fanatical statement that all of mathematics, including theory, all of human cognition is an image process are, surprise, surprise, are the logicians. And because the logicians point out, well, you say that all of mathematics is a Turing machine and everything is representable in this way, but what about stuff that's not representable? Well, in any standard way, there are numbers in which you simply cannot conceive of a way to represent them. I said, that's kind of interesting. And my fanatical way tells me that the unpresentable numbers have ways to be described, which can then be turned into an image. Right. But I think that is true. And I think that would be very interesting to try to see undescribable things and how they respond to machine learning. But I think that's a separate project. So then again, we played a lot of stuff after I went these colorful things, and then my former student Kieran Bull, this guy eats 5,000 lines of Python for breakfast, and then was able to do like more sophisticated things with this. So I'm not gonna bore you with any of it. It's just too boring. Lots of people doing lots of wonderful stuff. There's a whole community now. In starting with as I mentioned in 2017 when we were mucking about with Sophia, and then since 2017 2018 there's a whole community of string algebraic geometers doing machine learning, and now this community has even grown more to include other random fields of mathematics. And in the last 30 minutes, I'm just going to give you some more speculative thoughts, especially on something that really surprised me, which is how well it was doing in this paradigm is doing in number theory, which is, I guess, in what's closest to my heart. So I won't bore you with Siamese networks. You can ask Shailesh all about those. So so this is me, the fanatic, coming out, right? You know, why should you just stop at string theory and geometry? If you have this tool, this new tool, well, so why not learn all of mathematics, right? I mean, what prevents you? And then can you create a hierarchy of problems in mathematics where machine learning is hard and where machine learning is easy, right? So this now has gone in the last 2-3 years, it's gone under the general name of AI-assisted mathematics or AI-driven mathematics. And I want to make a huge distinction of how AI makes this difference. I like to call it the 3 ways that we do mathematics, including theoretical physics, of course, is bottom up, top down, and meta, right? So by bottom up, I mean in the sense of Russell and Whitehead. It goes to this Hilbert's formalization program, right? You know, how do you build mathematics from ground up, right? Oh, by the way, I highly encourage you to do this. Go online and type Hilbert, we need to know, we must know, right? This famous saying. What is truly amazing, you hear a 1930 radio address in the voice of Hilbert saying this. It's like 4 minutes, and it's one of the most amazing things I've ever heard. Just to hear the voice of God, right, and a saying that we need to know, we must know. But so Hilbert famously said this because he was inspired by Russell and Whitehead and how to build mathematics from foundation up. But this whole program was killed by Gödel, Church and Turing, because of incompleteness theorems. You know, they are statements which cannot be proven. But I like to quote my friend Min-Young Kim, who says, you know, we don't think about Gödel. Like, we don't really think about Gödel. I mean, it is possible that in your research, you may have wondered whether you have certain statements which is undecidable. I thought about what it occurred to me like once in my entire life, and that was with quiver gauge theories. And you know, at some point I was thinking about when Ami Khanani who was my PhD supervisor gave me this problem of, you know, classifying quiver gauge theories. This is what I was doing for my PhD thesis. I actually thought about, you know, is it possible that the classification of quiver gauge theories is a Turing incomplete problem? Is it undecidable? Actually, it turns out that it is, right? If you want to classify all quivers, it is actually Turing incomplete. So recently, people have been thinking about this more seriously. I think Jim Halverson and friends have been thinking about this. You know, the string landscape is undecidable because it has many subproblems which are just undecidable. Even simple things like to give a classification scheme of quiver gauge theories without the constraint of certain vanish and beta function. You know, if you just want to do it in general, that's an undecidable problem. So that's kind of interesting, right? But seriously, we don't really think about it, right? I mean, we do our computation without thinking about, oh God, is this statement even provable, or is this equation derivable? So, but that is an important thing, is because there is this ATP program. And this is a program which really goes back to 1956, which is kind of interesting. This is the same, almost about the same date as the first perceptron. You know, when people were building neural networks out of like cadmium sulfide photoreceptors, it was genius. And these guys were using that kind of computational skills to prove certain sets of Principia Mathematica as logical symbols, which is pretty impressive for 1956, right? And this has grown a lot. And I won't say very much because I'm tangentially involved with this bottom-up community. There's a huge community now called Lean, especially, and have and in particular the Xena project, which is spearheaded by Kevin Buzzard at Imperial, who, you know, because it's 40 minutes away by foot, which by London standards is next door. He comes from here time to time, and he's a fantastic guy to talk to, extremely knowledgeable. The Xena project is to take the entirety of undergraduate level mathematics and put it into this Lean software system, like line by line. This is a system of, I mean, it's a database thing. in type theory language. It's formalization of every single statement, every single proof of statement. And Xena project part 1 has just finished last year. So they actually have the entirety of undergraduate level mathematics in Lean. I mean, it's millions of lines, right? If you think about, proving everything from, I don't know, showing, proving Stone-Weierstrass convergence theorems to, showing that the hydrogen atom splits to this. They don't have that much physics in it yet, but, it's a lot. It's millions upon millions, tens of millions. But Buzzard has, the Lean community has a very big secret tool, which is called large parallel clusters of graduate students. So they have hundreds to thousands. Even in London, they have like something on the order of 500 in the Lean community who they just do it. I'm going to type 1,000 lines tonight or this week. You do it. So within 1 week, you can get something on the order of 1 million lines of code, and they cross-check it. And the good thing is that they cross-check themselves, right? And Lean, they just ran it, and they checked that all of undergraduate mathematics is self-consistent. So there's no contradictory statements. But undergraduate mathematics is less than 0.000001% of known mathematics. So the Xena Project 2 right now, this year, they just started last month, is inputting everything that's needed to prove Fermat's last theorem. And this is a fantastic project. So every single step, definition of elliptic curve, the whole spiel, the whole thing, to understand Walsh's proof. What's the modular form? That should take. So Kevin Buzzard has a 5-year grant on that, which should finish within 5 years. If not, get another 5 years. What I really would like to see, Xena Project 3, Part 3, is I would really like to see is the classification of finite simple groups. This is actually one of the foundational results in all of mathematics. There's 26 sporadic groups. Why is it 26? Have we missed any? Apparently, I know this community very, very well. I talk to them a lot. And they tell me, I mean, this is the community telling me, no human has actually read the proof of this classification theorem of finite simple groups. Nobody's checked it because it's over 10,000 pages. It takes longer than the lifespan of a human to actually digest that proof. So you have to check this by computer, but it hasn't been done so far. The Kepler conjecture has been checked in Lean by Koch in 2017. So obviously, after Walsh's proof, which has been checked by humans and we know it's true, we got to do the entirety of the finite simple groups. But just to give a time scale, and this is also a very important thing, of fact, and Kevin is totally on board with this. Even typing this data in some form or another, even if you use OCR, is not in the immediate future that this is going to be doable. I don't know what the time scale is. So let's think about it. So his grant is 5 years for just Fermat's last theorem, right? So just scale that up, right? So all of this stuff about AI, oh my God, you read in the New York Times, AI is going to replace humans. AI is going to replace the human mathematician. It's not going to be any conceivable near future, because even typing in this database, even with OCR recognition and cross-check that, we're not even near that. So this estimate by DeepMind in 2030 is very, very optimistic. You may get some interesting theorems, but it's not clear that this is going to be anytime soon. So this is
when people input these theorems into this Lean thing, is it kind of the way you read it and then it's like human readable input, or there's a special language that they have to use?
It is completely unreadable.
Okay.
It's completely unreadable. So I can give you a sample of this. It's actually kind of nice. So here's a really good, so it basically looks like this. Let me just show you this. Can you see, or
we still see your screen, your slides.
Okay, so I'm going to stop sharing 1 minute. I'm going to share this share. Right? So here's yeah, here it is. This is the Lean code to prove, I don't know, some like something about a circle. This is baby step number one. I can't read it. I'm not versed enough to look. I mean, it's not human readable.
But the language, this language that they're using is in principle powerful enough to capture any statement you want to make in mathematics.
That's exactly the point. Yeah, in principle. In principle. But it's certainly, and the trial is that it's powerful enough to have now already completed the undergraduate curriculum, which is not bad. And there are some more interesting stories, like no, sorry, share screen, which is a recent success story, two success stories, which is when Peter Schulze had a proof of something, and then he went to Buzzard to check it. He wanted this to be checked. And he turned out to be right, of course, because he's Peter Schulze. But in the process of inputting the intermediate steps of his proof, they found a shorter pathway towards his proof, which is kind of nice. And I think it was just a few months ago, there was a collaboration of Gowers, Manners, Tao, and Green. When you have a collaboration that has 3 fields medalists, this is serious stuff. So they went to Lean, and they were able to extract, to get enough out to prove one of these polynomial Kutsha conjecture, something combinatorics, which is a new theorem. They were able to get the proof of that. So that's kind of nice. So this bottom up is very much alive. This bottom up, I'm not really involved in this community, but it's a community that goes back to at least 1956, and it's doing great. The other community is what I call this meta mathematics, which is to just not to think about this as mathematics at all. If you have absolutely no idea what's going on, like ChatGPT is doing, just treat every single statement of mathematics as a large language model, right? So, here's a fun thing. This is great. And since Vishnu is in the audience, I can have, so this is one of the fun things I've ever done in my life, which is to write this back in 2018, when we learned about Word2Vec. So I learned about Word2Vec. I told Vishnu and Brent Nelson, I said, dudes, we got to LLM the archive. This is totally cool, because, this is 5 years ahead of what DeepMind is doing now. Take the archive, and the fun, we found some linguistic stuff and whatever. But the thing is that the best part of the project, we compared the archive to Vixra. We took the titles, because at the time we didn't have a LaTeX scraper that was powerful enough to scrape actual text. But you can actually see that in archive, even from the title, there's the vector space of linguistics in archive in its different sections are self-consistent. HepTH, the confusion matrix between HepTH and GRQC is different, even though they have the same buzzwords very often. HepTH and HepPH, GRQC are different. Whereas in Vixra, they're completely muddled up, because, in Vixra, it's basically a string of words, quantum gravity, black holes, Stephen Hawking, Penrose, But in archive, the same words appear with the same frequencies, but they're even at the title level, they are arranged in an order in sequences that when you do the classification on a confusion matrix, different subfields are different. So I go and tell people, look, pseudoscience really is different, because crackpots have no idea what they're saying. This is a very good LLM statement about what science is, but this can be taken much more seriously, right? If you think about, I won't bore you with this, but if you think about what one of the greatest triumphs is, that in 2022, ChatGPT has actually passed the Turing test. If you talk to ChatGPT, it's indistinguishable from talking to a stranger, which is a bit worrying, right? It's a bit unnerving, because he has no idea what he's doing. It's just doing a fancier version of Word2Vec or an autoencoder transformer. That's all it's doing. Just taking words and tells you the probability that a word is to the left is this word, to the right is this word. That's it. That's all LLMs are doing. It's a sequence of words where there's a probability distribution for each word to its left and to its right. And the greatest triumph is, well, Q star is yet to come from OpenAI. But what is really a triumph in this direction is DeepMind's, the one that just came out. Sorry, I haven't updated this reference, which is AlphaGeo. So this is kind of interesting. So AlphaGeo is takes the proofs in human readable form of all of the solutions, standardized solutions to the International Math Olympiad Euclidean geometry problems. So you give a diagram and it shows you it needs to prove this. And it just did an LLM on that. And now it could answer like something like 60 to 70% of LMM of Math Olympiad questions. And it's doing that, it's just doing exactly by doing an LLM on previous solutions. It has no idea what it's doing, but it's spitting out human digestible forms as if a student would do it. It's not succinct, but if you give it to a very, very clever IMO candidate, he or she can actually look at this and follow the proof of such statements. So which I think is quite amazing. So this is AlphaGeo, which just came out last month. So obviously, I think even in their paper, in DeepMind's paper in AlphaGeo, they mentioned it is clear what we need to do. We need to apply this LLM model to the lean database of all of mathematics, and that should be able to generate new proofs of new theorems. Right? But that's in no time soon, because we don't even have that database yet. And Kevin Buzzard tells me we got to, even his large parallel clusters of students, it will be working day and night. It'll take a long time to even just get in all of the statements of Fermat's last theorem. That's just one statement. So it's going to be a while. So we're safe. Don't quit your job yet. We're safe, at least I think within our careers. And then if you have lean database to the entire archive and then do LLM on that, then we're really in danger of like losing our jobs. But that's not anytime soon. But the stuff that I write, but what is making huge strides? So I've told you about great strides in bottom up and top down. The ATP program with the LLM program, they're both going great, but they're no threat to humans yet. And now the one that I like to talk about is top down. This is sort of intuitive art. So mathematics is an intuition, right? So this kind of stuff that I've been telling you about, how do you give to John Mackay some numbers and he can tell you a story? Or how do you give a picture to Philip Candelas and he says, well, these are clearly mirror pairs. How do you imitate that process of discovery? So this, you can formalize this by saying this is conjecture formulation, right? So the best conjecture formulation machine of the 19th century, the best neural network was clearly the brain of Gauss. Where Gauss at the age of 16 was able to look at this diagram and says clearly x over log x. This is a plot of the prime counting function, the number of primes less than or equal to given real number x. Don't forget the BSD conjecture was Birch and Swinton died in the 1960s in the basement in Cambridge somewhere. And they had a machine the size of a room, and they just plotted conductors and ranks of elliptic curves. They did a similar thing, and this is still an open, right? So these are central problems in mathematics where people could just look at certain diagrams and say, well, this is clearly this, and then you need to prove it. Right? I have no idea why Gauss Gauss is Gauss, right? What can we imitate Gauss, right? So the idea is like LLMs applied to Principia Mathematica should clearly determine the future of mathematical research, but not near future, but it's certainly going in that direction. But there is a part of mathematics which is completely not this. It's just like random firings of neurons to look at pictures and then make profound conjectures. But that is something that the AI can do fairly well, right? So if you take here's a great example. If I give you this sequence, you can tell me what the next number is, right? Well, it's just 3 or not, right? If you tell me what the next one is, you struggle after a bit, you can tell me that it's prime or not. If I give you this sequence, you're pretty hard pressed to tell me what the next number is. This is the number of prime factors, the parity of the number of prime factors of integers up to multiplicity. If you can tell me the next number greater than 50% confidence, you will prove the Riemann hypothesis and crack every bank in the world. So like forget about collecting the 1 million Millennium Prize, because then you will know something about primes that nobody knows about. And so one thing you can do to data like this is to do exactly what I just did earlier with Hodge numbers, right? Feed into neural network. You can standardize in some way. One way to do it is to do a slide rule, take a window. So a hardcore sequence prediction isn't great. So if you want to feed one of these into a recurrence neural network, you're not going to get immediate results because it's kind of the feature space is not very rich. But one thing you can do is to take a window, say 100 or 50, whatever, and then slide it 1, 1, 1, and then try to predict the next one. So now this becomes a supervised machine learning problem, right? So this is one that predicts the numbers 1. So for example, if you take the first 100 integers, up to 100 is not prime, but the next one, 101, is a prime. And you slide along the 102 is not a prime, so on and so forth. But now this is interesting. This becomes a labeled data set in dimension 100. And there's no way that even Gauss couldn't like picture this, right? The one thing that's better than the brain of Gauss is looking at dimension 100. So we kind of, in mathematical conjecture formulation, we're turning a disadvantage into an advantage. We're turning the curse of dimensionality into the blessing of dimensionality. Because if, any simple conjectures at this point, if it's a simple conjecture, some human would have just spotted it, right? It's just almost impossible now. If you want some profound conjecture that relates to primes, you need to go up in dimension. So then you feed one of these suckers into your favorite classifier that I've been talking about, forward, I clearly, by the way, of course I tried this on every single neural network I think of, a convolution network, and try, because I was trying to break the 50% and then break every single bank and never be seen again. But the fact that I'm still talking to you means I did not succeed in that. So, and if you try this, you can very readily see that the multiple 3 problem, 100% accuracy, like in seconds. It's just stupid, right? This is a linear transformation. And then the prime ones, you struggle a little. In this one in particular, I could not find anything that breaks the 50%. So here's a challenge to you. If you can find a neural classifier or any regression analysis, decision tree analysis that can predict the next number to better than 50%, even a tiny bit better than 50%, and you can interpret why it's doing that 50% and write down that interpretation, let me know. And let's crack some banks together. So obviously, I got a few, let's see, I don't want to take your lunchtime away. So you can do this because all of mathematics is this, right? Because, Turing machine accommodates all possible computable mathematics. So just take your favorite data set in mathematics and do it in this form, right? So in the last 7 years or so, I've made friends with every community that I can think of. I think some Vishnus in the audience, I'm good at making friends. This is like the only gift God has given to me. It's like I like hanging out with friends, especially over a drink. And I highly encourage you guys to have a drink with Vishnu because he's a cool guy. I won't bore you with any of this, but I'd like to mention the bit about all of you can do, this conjecture from me. So I'm going to skip all of this. I'm just going to basically go back to summarize what I'm trying to say. So in these three directions approach, right? This is the bottom of the lean, Koch, Zeynep systems. They're doing great. They're building mathematics up, and that's surely going to happen together. The LLM approach, deep mind approach, is definitely going to happen. And one very active one is this top-down in conjecture formulation, right? So let me just finish up by telling you how far. So good, but limited. This one, surprise, surprise, is also good, but limited. You would think that by this point, if you start feeding in freely available mathematical data, some clever neural network will have made a prediction as profound as Gauss. But so far, none of them nothing have happened. So let me just give. So here's a funny thing, right? Let me give. I won't give you some. So you got to give a name. So last year with Suresh, I think who's known to you, who's really he really did all of the organizational work, which is to have there's another. The title is so long for the Isaac Newton Institute that they cut off the last bit, but it's supposed to be black holes, bridges between number theory, holographic quantum information, algebraic geometry, and machine learning. So it's basically everything, including your grandmother's kitchen sink. But the whole point is that this was to create a forum for every expert from every field that's interested in data to talk to each other. So Kevin Buzzard is there, Albrecht Clem, and Robert de Malakoff. I think you know these are people now. So in there, we're inspired by watching a video of Brian Birch, and we try to formalize this conjecture formulation approach of AI to mathematics, right? So if it's a conjecture, and when do you pass this strict test, right? You got to name it. We called it the Birch test. This is, of course, a reference to Turing test, which ChatGPT did pass in 2022. So the test is that it has to be entirely generated by AI. You can't have our humans mucking about in the middle to guide it here and there, right? You feed the data in and run away, have your coffee. 2, it must be concrete enough to be a conjecture, right? That it must be interpretable. That this pretty much kills all neural networks, right? 3, it must be non-trivial enough for the community to actually work on, for humans to actually work on it. So this is the 3 Birch tests. And most of all, you got to make Birch happy. Birch is 94 and looks pretty happy to me. But the point is, everything that's been done so far has not passed the Birch test, right? Delete, this stuff that I was mentioning in these early experiments, Hodge numbers, it's not interpretable. Neural networks say, even if it does to 99.9999%, but what is it telling me? It's not giving any new information to the mathematics and physics. There's some simple groups, I won't bore you with this, and some on graph theory, not interpretable. This really famous paper of Davis et al. This is a DeepMind paper on Nature in 22 about knot invariance. And oh, by the way, there is similar very nice work on knots by Gukov, Halverson and friends, and also by Vishnu and friends. But here you suffer the problem is that you have a combination of either not interpretable or not non-trivial. In this one, this is highly publicized. They were able to extrapolate a new relation among the knot invariants in the dependence of the Jones polynomial. Through a very clever thing they did a saliency test. They conjectured this. They did, what are the possible features the Jones polynomial can depend on? They were able to get this, and then they did a regression analysis on the salient features, and it turned out that it was a linear regression. So they're able to conjecture a new formula that nobody has seen before. The thing is that the conjecture was not non-trivial enough because it didn't make anybody work on it because they were able to prove themselves within a month. It's a new relation, but it's a linear relation that's not known to them, but you're able to prove it. And similarly with the case, there was a paper by Konstantin and Lucas on computing the line bundle cohomology on surfaces. They were able to inch out a precise formula, but again, you can check it by sequence tracing. They were able to prove that formula. Final dimension of final quantum purity. This is a paper in Nature Communications. But again, it was because they used a deep neural network, they were able to extract features, but it's not interpretable. The only one, to my knowledge, that's passed the non-triviality test. So this is one that's a fun project we did, which is, it finds a new Clavial, but it was non-trivial. People were like, oh, wow, this is a new result. The only one that I know of that has, and I checked this, so this is not a shameless self-advertisement. The only one that's passed the non-triviality test, so this is Birch 3, is the murmuration conjectures. This is done in joint work with number theorists, Lee, Oliver, and Potsniakov, and then with Sutherland, who created the database, the online database. This is what I'm so excited about number theory, and it made Buzzard happy. Buzzard said this is a non-trivial result, and Birch. But the problem with this, it fails straight away. It fails Birch 1. We simply did not take, elliptic curve data and then had a cup of coffee. We tried everything under the kitchen sink, and it finally surprised. This is why I spent some time explaining to you what a PCA was. At the end of the day, so I won't bore you with this, but it was you can predict the ranks of an elliptic curves using the data of the Euler coefficients in this L function. This is very interesting, right? You expect to do so because BSD underlying tells us that this should be the case, but nobody knows of an exact formula of the rank of the elliptic curve in terms of the A's. We know there should exist one, but we don't know what it is, right? So if you know what it is, you'll end up proving the BSD and you get $1 million. So but we threw in these coefficients and it was able to predict the ranks. We used anything. We used a deep neural network and it was able to predict rank very well. But at the end of the day, we used a good old-fashioned PCA, Stats 101, and it projected to this. And this is pretty good separation, right? There's some error, but it's pretty good separation. The point here I want to emphasize is that PCA was good because what is it? We took 100 Euler coefficients in elliptic L functions. Here's a feature space in 100-dimensional, but PCA projected this to a 2-dimensional, so you can visualize it, and it's a linear transformation. So we could look at the weight matrix, it's a 100 by 2 matrix, and see what it's actually doing. So already this fails miserably Birch 1, right? Because I started at the end of the day, it was like, oh wow, this is so cool that support vector machines, decision trees, neural networks could all do this classification problem so well. But there's no surprise because we know BSD has to make this true. And furthermore, we know Bhagava's result, which got him into Fields Medal, is that 50% of elliptic curves and 50-50 are distributed to a 0-1. And if you go even further than that, and it's proven the BSD conjecture for rank 0 and rank 1 elliptic curves anyway. But the surprising bit was that when we finally settled down to PCA analysis, we started giving Postnikov, who was a wonderful guy. He was a second-year undergraduate at the time. So we gave him like hundreds of these 100 by 2 matrices for him to look at. And he was able to spot with a human eye that a lot of the focus of these weight matrices was in a single column. What does it mean? It means that the PCA is essentially doing an average. So this average is now known as a vertical average. So now here's a formula. So now forget about machine learning. It just says if I give you within a certain conductor range of elliptic curves, you go to a number theorist and tell the person this, right? I give a conductor within the conductor range of elliptic curves, average over different elliptic curves, average over different isogeny class of elliptic curves, and plotted against primes. This is surprising because this is not something you would usually do. Normally, people average over the primes over a fixed elliptic curve. This is an average over different elliptic curves. And you plot it, and it shows there's this separation. And these curves, the conjecture is that these curves are different and they converge to specific curves. And that actually was a completely new phenomenon to the number theory community. So people like Sarnak started working on it. And is now being proven for certain cases. So this is certainly non-trivial. It's certainly non-trivial to me because I'm a novice number theorist. But if Sarnak says he's never seen it, and Sutherland says never seen it, and that means that a combination of human and AI was able to raise a new completely precise conjecture in mathematics. And that here it is, showed that this curve converges in the limit of large n. And there are more features. It actually turns out to be a scale invariant curve, which is kind of really, really pretty result. And so Zubrylina and then the number theorists have actually proved for weight 2 modular forms. So then now it's a theorem for 2 cases, and people are still working on it to show that this is the case. So this passes Birch 2 and Birch 3, but it fails Birch 1 miserably because essentially it was AI-guided human intuition. Nevertheless, I just like to draw you guys to this nice thing, like 19th century, human eyes were good enough. 20th century, you need computer help. 20th century, this AI-guided human intuition is certainly the way to go forward. So I think it is safe to say that the future combination of what mathematics, and by mathematics I mean in the British sense, to include theoretical physics, all of us, is that AI will be transformative in all three approaches to what we understand theory to be. So I think I'll stop here and let you guys go to lunch.